Welcome to Mind Mechanics Lab, where we decode the most fascinating stories from history, science, and the world around us. Today's discovery will change how you see things. Let's dive in. What if I told you that for centuries humanity looked up at Mars and saw something completely different from what science tells us today? We're not talking about little green men, but something far more intriguing for the mind that seeks to understand reality. From the mid-17th century, when Mars's polar ice caps were first spotted, to the late 18th century, when William Herschel observed their seasonal growth and shrinkage, our fascination with the red planet has been intense. By the mid-19th century, astronomers knew Mars had days almost as long as Earth's, and a similar axial tilt, giving it seasons, though nearly double the length, due to its longer year. These striking similarities fueled a cascade of speculation. People imagined its darker areas were vast oceans, its brighter regions land, and naturally, they wondered, could life thrive there? In 1854, William Whewell, a Cambridge scholar, theorized Mars had seas, land, and possibly even life forms. Then, in the late 19th century, speculation exploded with telescopic observations of what appeared to be Martian canals. This wasn't just a casual thought. It became a pervasive belief, driving astronomers like Percival Lowell to publish books like Mars in 1895 and Mars and Its Canals in 1906, proposing these were the work of a long-gone civilization. This powerful human tendency to project our desires onto the unknown, to fill gaps with compelling narratives, is a fascinating aspect of our psychology. And it laid the groundwork for sci-fi classics like H.G. Wells's The War of the Worlds in 1897. But what happens when hard science clashes with compelling stories? That's where the real mechanics of discovery begin. The Martian Canals theory was a powerful narrative, but like many compelling stories, it eventually met the unyielding force of scientific inquiry. In 1907, British naturalist Alfred Russel Wallace published Is Mars Habitable?, directly refuting Lowell's claims and concluding Mars was absolutely uninhabitable. This was a pivotal moment, marking an early work in astrobiology. The optical illusions of canals began to fall out of favor, especially after Eugene Antoniadi's observations in 1909, with the 83 centimeter telescope at Meudon Observatory revealed no canals, and outstanding photos from Pic du Midi Observatory further discredited the theory. Meanwhile, spectroscopic analysis starting in 1894 with William Wallace Campbell showed no water or oxygen in the Martian atmosphere, further dimming hopes for surface life. So why does Mars remain such a focal point for the search for extraterrestrial life today? It comes down to its incredible similarities to early Earth. Mars has a cold climate and lacks plate tectonics, meaning much of its surface has remained almost unchanged for billions of years. At least 2/3 of it is over 3.5 billion years old. This ancient, relatively untouched surface means Mars could hold the best record of the prebiotic conditions that led to life, potentially even existing 4.48 billion years ago, a staggering 500 million years before the earliest known Earth life forms. Understanding Mars isn't just about finding aliens, it's about unlocking the very secrets of life's origins, a challenge that demands the utmost scientific rigor and an unwavering commitment to data over dogma. The core idea that drives modern Mars exploration isn't about looking for advanced civilizations. It's about searching for the building blocks and conditions that could support microbial life. The scientific consensus today is far more nuanced than the 19th century canal theories. Cumulative evidence strongly suggests that during the ancient Noachian time period, Mars's surface environment had liquid water, meaning it may have been habitable for microorganisms. This is a critical distinction. Habitable conditions do not automatically equal life. The surface of Mars today is a far cry from that ancient, potentially watery past. It's bathed in ionizing radiation, and its soil is rich in perchlorates, which are toxic to microorganisms. Therefore, the current scientific consensus posits that if life exists or existed on Mars, it would most likely be found or best preserved in the subsurface, away from these harsh present-day surface processes. This understanding has profoundly shaped the objectives of space agencies. The search for evidence of habitability alongside the hunt for fossils and organic compounds on Mars has become a primary goal. It's a testament to the scientific mindset, constantly refining hypotheses based on new data, shifting focus from visible surface features to the molecular and geological signatures hidden beneath. This systematic approach, moving from broad speculation to targeted investigation, is a powerful mind mechanic for tackling complex problems, whether in astrobiology or business strategy. Today, our quest for Martian life is driven by an impressive fleet of robotic explorers. Rovers like Curiosity, Perseverance, and Opportunity have been tirelessly searching for evidence of past life, meticulously analyzing the Martian landscape. Their findings have been revolutionary. We now have confirmation of the past existence of surface liquid water, with evidence of fluvio-lacustrine environments, plains related to ancient rivers or lakes that may have been habitable. Even more exciting is the discovery of organic compounds inside sedimentary rocks and the presence of boron on Mars. These are not direct signs of life, but they are crucial precursors for prebiotic chemistry, the very chemical reactions that could lead to the formation of life. Such findings, combined with the clear evidence of liquid water on ancient Mars, strongly support the possible early habitability of Gale Crater. But the evidence doesn't stop there. In June 2018, NASA announced the detection of seasonal variations of methane levels on Mars. Methane is intriguing because it can be produced by microorganisms, but it can also be generated by geological means. This ambiguity is precisely what drives further investigation. It's a classic example of how scientific evidence often raises more questions than it answers, pushing researchers to design new experiments and missions. The pursuit is relentless, fueled by these tantalizing clues, constantly pushing the boundaries of what we know about our cosmic neighbor. This relentless pursuit of answers on Mars offers a profound lesson in the mind mechanics of high-stakes endeavors. Think about the scientific method itself. It's a powerful framework for decision-making, moving from hypothesis to evidence, constantly refining our understanding. It's about overcoming deeply ingrained prior beliefs, like the Martian canals, with objective data. This demands immense perseverance, a trait crucial not only for scientists, but for anyone tackling ambitious goals. Consider the European ExoMars program, which saw its Rosalind Franklin rover's drilling plans indefinitely suspended. A major setback, yet the commitment to the long game, like NASA's plan to return Perseverance's cached samples in the late 20s or 2030s, remains unwavering. This patience, this multi-decade vision, is a powerful psychological mechanism that allows for monumental achievements. The psychology of uncertainty is also at play. The methane detection, for example, isn't a definitive yes for life. It could be biological, or it could be geological. This ambiguity, rather than leading to despair, fuels further inquiry, demanding more data, more missions, more analysis. It's a critical business lesson. True innovation often thrives in the gray areas, requiring deep analysis rather than premature conclusions. The business of science here is about long-term investment, international collaboration, and the unwavering belief that understanding the origins of life is a worthwhile, indeed essential, human enterprise. The continuous investment in Mars missions showcases a real-world application of this scientific mindset. The European ExoMars Trace Gas Orbiter, for instance, began mapping atmospheric methane in April 2018, providing crucial data to understand the mysterious seasonal variations. While the Rosalind Franklin rover's drilling mission faced suspension, the commitment to subsurface analysis remains strong with NASA's Perseverance rover. Having successfully landed, Perseverance is meticulously caching dozens of drill samples, preparing them for an unprecedented journey back to Earth laboratories in the late 2020s or 2030s. This isn't just about collecting rocks, it's about bringing potential evidence of life, or the conditions for it, to the most advanced labs on our planet. The progress is incremental but impactful. In October 2024, NASA announced a fascinating possibility. Photosynthesis might occur within dusty water ice exposed in Mars's mid-latitude regions. This expands our understanding of where and how life, even in its simplest forms, could potentially endure or thrive on the planet. And then, the tantalizing news from September 2025, NASA reported that Perseverance found a possible biosignature in a Jezero crater rock the previous year, hinting at ancient microbial activity. These are not definitive proofs, but they are powerful indicators, each step refining our understanding and shaping the future of space exploration. It's a compelling narrative of persistent effort, where each small discovery builds towards a larger, epic-making truth. The human drive to explore and push boundaries, often seen in ambitious business ventures, is perfectly mirrored in this scientific quest. While the evidence for past habitability and potential biosignatures is exciting, the scientific community maintains a healthy skepticism, recognizing the immense complexities involved. Defining habitability on Mars is far from simple. It's not just about one or two factors. Scientists use 19 or 20 environmental factors, emphasizing water availability, temperature, nutrient presence, energy sources, and protection from solar ultraviolet and galactic cosmic radiation. Isolated measurements aren't enough. It's the sum of these factors that truly predicts habitability potential. Laboratory simulations reveal a stark reality. When multiple lethal factors are combined, survival rates for Earth microorganisms plummet quickly. Crucially, there are no published full Mars simulations that include all these biocidal factors combined, underscoring how much we still don't know. Furthermore, there's the open question of whether Martian life, if it exists, would have a far different biochemistry and habitability requirements than terrestrial life. A common hypothesis involves methanogenic Martian life, which, while present on Earth, is exceptionally rare in environments with oxygen. The challenge is immense. Surface radiation and perchlorates make life on the surface nearly impossible for known organisms. This complexity demands extraordinary rigor. The scientific process isn't about quick answers. It's about acknowledging nuances, understanding limitations, and meticulously working through every layer of uncertainty before drawing conclusions. This is a critical lesson for any leader or entrepreneur. True insight comes from embracing complexity, not oversimplifying it. So what's the actionable lesson from humanity's centuries-long quest to understand life on Mars? It's a powerful blueprint for success, whether you're launching a startup, solving a complex business challenge, or pursuing a personal goal. First, challenge assumptions. Just as astronomers disproved the canals, you must question entrenched beliefs with objective data. Don't let compelling narratives overshadow inconvenient facts. Second, embrace long-term vision and perseverance. The Mars missions are multi-decade endeavors with setbacks and slow progress. Breakthroughs don't happen overnight. In business, this means committing to a vision far beyond quarterly earnings, understanding that sustained effort yields monumental results. Third, seek data, not just belief. The methane mystery on Mars reminds us that tantalizing clues require rigorous investigation, not immediate leaps to conclusions. Make decisions based on evidence, not just intuition or hope. Fourth, understand complex systems. Habitability on Mars isn't simple, it's a matrix of 19 to 20 factors. Similarly, in any complex system, whether it's a market, an organization, or a personal challenge, recognize that multiple interacting variables dictate outcomes. And finally, value incremental discovery. Each rover, each sample, each piece of data, no matter how small, builds towards a larger truth. Don't discount small wins. They are the foundation of major breakthroughs. Whether in business, science, or your personal goals, adopt the Mars mission mindset. Question, explore, persevere, and understand that true breakthroughs come not from fleeting speculation, but from relentless, data-driven effort. Thanks for watching. If you enjoyed this story, hit that subscribe button. New discoveries every Tuesday and Friday. Until next time, keep questioning, keep exploring.